The ARM Cortex-M0 processor is the smallest, lowest power, and most energy-efficient ARM processor available. The Cortex-M0 architecture was specifically developed as the first 32-bit microcontroller replacement for traditional 8 and 16-bit formats. Thanks to new process technologies, today's 32-bit microcontrollers fit in the same silicon areas as an 8 or 16-bit device, which means that 8 and 16-bit microcontrollers are losing their traditional cost advantage. The amount of memory that an MCU needs for program code can also affect the cost of a processor or the system design. The higher the memory requirement, the higher the cost. It may not seem obvious, but the 32-bit Cortex-M0-based LPC1100 offers superior code density compared to 8-bit and 16-bit architectures. It would be easy to assume that a 32-bit microcontroller would need 32 bits or 4 bytes for each instruction, and that an 8-bit microcontroller would need 8 bits or 1 byte for each instruction. That would mean a 32-bit microcontroller would need 4 times as much program memory as an 8-bit microcontroller, and 2 times as much program memory as a 16-bit microcontroller. However, this is not true. In fact, code size on a 32-bit Cortex-M0 processor can actually be less than the code size for an 8-bit processor, sometimes as much as a quarter or half as much. Let us start with an understanding of the Cortex-M0 instruction set. The Cortex-M0 is a RISC or Reduced Instruction Set computer architecture based on the ARM thumb concept. The complete instruction set for the Cortex-M0 can be seen in this diagram. Almost all of the Cortex-M0 instructions are 16 bits in length, but operate on 32-bit registers and 32-bit data paths. The only 32-bit instruction used in application code is the BL or branch with link instruction. An 8-bit architecture does not mean that the instruction length will be 8 bits, nor does a 16-bit architecture mean 16-bit instructions. This bar chart shows graphically how instruction length can vary with the processor architecture. For many 8-bit microcontrollers, instruction widths can be 16-bit or larger. For example, some 8051 instructions are 1 byte long, but others are 2 or 3 bytes. For the 8-bit PIC18, instruction sizes are 18-bit. For the 16-bit PIC24, instruction sizes are 24-bit. The instruction length of an MSP430, a 16-bit architecture, can vary from 4 to 8 bytes. Since the instruction set for the Cortex-M0 is mostly 16 bits, it's clear from this instruction width comparison that the code size for the LPC1100 has a good chance of being the same size or smaller than most 8 and 16-bit processors. Instruction width is not the only factor to determine eventual code size. Code size can also be affected by the width of the data the processor has to deal with. Let's consider an example where an 8, 16, or 32-bit microprocessor is receiving data from an integrated 10 or 12-bit analog-to-digital converter. To support basic filtering of the 10 or 12-bit ADC data, a microcontroller typically uses a 16-bit multiply. This table shows sample code for 8 and 16-bit microcontrollers, and our 32-bit LPC1100 for 16-bit multiplies. The Cortex-M0 uses only one 16-bit instruction for the operation, and executes it in just one clock cycle, while the 8-bit 8051 and the 16-bit MSP430 require more instructions. It's clear from this comparison that the code size for the LPC1100 will be much smaller than the 8 and 16-bit microprocessors. Our examples have shown that the code size for the Cortex-M0-based LPC1100 should be less than code size needed for 8 and 16-bit microcontrollers. An even more thorough comparison would be to use industry benchmarks. Therefore, NXP uses the CoreMark benchmark from EEMBC. This benchmark has a small footprint that is ideal for microcontrollers with small amounts of memory. CoreMark is designed to test for how efficient the processor is at fetching and executing code, performing read-write operations to memory, as well as integer and control operations. It should be mentioned that CoreMark only deals with core and not peripheral efficiency. CoreMark benchmarks are a good way to compare the core performance of different processors. Comparing the CoreMark per megahertz results of the LPC1113 with the 16-bit MSP430 and the 8-bit Atmel ATmega644. These CoreMark results also show that the LPC1100 outperforms the competition at the same frequency at a rate of 2 to 1. These results are plotted using the fastest compiler settings available for each compiler. CoreMark benchmarks can also be used to compare the code density between processors. Comparing against the same microcontrollers, we can see that not only does the 32-bit LPC1113 have better performance, it also has better code density than the MSP430 and significantly better code density than the 8-bit ATmega644P. Let us look at additional CoreMark comparisons. This chart shows that the LPC1100 code size is 54% smaller than the PIC24, 51% smaller than the PIC18, 49% smaller than the Atmel AVR8, 44% smaller than the Renesas H8, and 16% smaller than a generic MSP430. In summary, although it may seem intuitive that an 8-bit microcontroller would have smaller code density than a 32-bit microcontroller, the opposite is true. The 32-bit LPC1100 family often has smaller density than 8 and 16-bit microcontrollers. At the same time, the LPC1100 offers significantly more efficient performance.